All right, I got the note saying we're recording. Okay, so here we go. We are officially recording. So chapter 17, we are going to, I guess I realize now that I covered a lot more than I thought I would for this chapter. Okay. So chapter 17 deals a lot with language of a hypothesis testing. I think I gave you some really good practice homework and I should have told you guys, it didn't need to be turned in because and it just didn't need to be turned in, but it was good practice. So we kind of gave a similar example last time. You have a friend have a game with a coin flip. Heads you win, tails your friend wins. The coin comes up tail, 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 tail. Is your friend cheating? What would be the probability of 5 tails in a row? And so we talked a little bit about that yesterday. Basically, it's about 3%. So if we perform this experiment 100 times, 5 times, it will come up with, actually, this should say 3 times. 3 times, it will come up with 5 tails in a row. So it is unlikely, but it is possible for that to happen. So the null hypothesis, as we mentioned yesterday, is a statement of no change, no effect, or no difference, or a fair coin. The null hypothesis is always assumed to be true until evidence indicates otherwise. It almost always has an equal sign. There will be one exception to that rule when we start talking about the chi-square test, but for our class, it almost always has an equal sign. It's often not stated directly in the problem. It's often implied, and so that's what makes it a little bit hard. It is always about the parameter. It is never about the sample. So examples would include, so you should, in your null hypothesis, I've actually give you a few more. P, mu, sigma, the letter D, R, we can do we don't often do a correlation coefficient hypothesis test, but you can do them. And we can also do them about the slope. So M would be another examples. So we would not use P hat, X bar, the letter S, D bar, R hat, or your beta. So the alternative hypothesis, kind of as we mentioned yesterday, statement we were trying to find evidence or support. It's often stated in the problem. It's usually stated in the problem. So we have three different types of hypothesis tests. You have a two-tailed test, a left-tailed test, and a right-tailed test. So with the two-tailed, with all 3 cases, your parameter is going to equal some specific value. And then you just have to decide, is it going to be a not equal? Is it going to be a less than? Is it going to be a greater than? So do you guys feel pretty confident about picking that out, especially after I gave you that practice homework to do?
Yeah, the practice homework was really helpful.
Okay. All right, so let's go ahead here. Make sure you guys are really good at this. Determine the null and the alternative hypothesis, and is it a one or a two-tailed test, okay? So a pharmaceutical company has just developed a new antibiotic for children. Other similar antibiotics show that 2% of children experience headache as a side effect. The FDA wants to know if your antibiotic is more than 2%. So what would be your null hypothesis and your alternative?
It equals 0.02. The HO equals 0.02.
Okay, so HO equals 0.02 only gives you half credit. And I know a lot of people like to do that because they don't like to pick a letter. But if you want half credit, you can do that, I guess.
Would you choose P?
Why would you choose P?
Because it's a percent.
Yeah, so we got to be careful about percents. It's a proportion, is what I would say. Because some percents can be considered means, and some are considered proportions. And so the way to think about that, percents are, let's see here. Percents are often proportions, but proportions are not. Well, let's put it this way. When I'm talking about a proportion, your proportion is always out of 100%. Okay, so if it's out of 100%, we're going to use the letter P. Now, let's talk about like a stock market. You can gain more than 100% in the stock market, right? You could get a 200% return, or you could get a negative return. You could lose money. You might lose 55%. Okay. In that case, even though it's a percentage, you would treat that as a mean, and so in that case, you'd use mu. But yes, when we're talking about 2% of children experience side effect as a headache, you can't get more than 100% of children having a headache, right? So does that make sense, the difference between a proportion and a mean?
I have a question.
Okay, go ahead.
So if it was like the mean score on a test was 85%, the professor thinks that the mean score something could have been 86. It's a percent, but would you still do mu because it's a mean?
That's a good question. And I wish I had a poll thing that would say, hey, can everybody vote? But how would you guys think about that? Would that be a mean or a proportion?
A mean?
So Rachel's going with mean. I really wish I had a poll here. In one of my other jobs, we do this. Who says it's proportion? And who says it's the mean? Give me a thumbs up on what you think it is in the chat. Can you see the chat?
So put our answer in the chat.
Yeah, just give me a thumbs up. If you think it's a proportion, give me a thumbs up on proportion. And if you think it's a mean, give me a thumbs up on the mean.
Can she repeat the question?
So 85% on a test, and the professor thinks that they scored higher than that. Okay, it looks like it seems to be mean. See, I would go with proportion. Why do you think it's a mean, Rachel?
Because it says mean. Like the mean.
It says it in the problem. Is this a specific problem?
Well, no, I just made it up. That the
you just made it up.
score of a test was 85. And the professor thinks whatever, some other thing.
Some other thing. So that one's a tricky one. You could kind of argue it both ways. I would say proportion because typically what's the high score on a test? High score you can get.
100%.
Yeah. Now maybe the professor has some extra credit, but it's, so technically maybe they could get more than 100%, but typically on a test, you're looking for the proportion of correct answers out of 100%. So I would go with proportion on that one.
So the only time it would be a mean is if it went over 100% somehow.
Yeah, that's why I kind of gave the stock market example, because that's probably the most common example of somebody you could get a 150% return or a 200% return, and that's a legitimate number. You can't get 200% on the test. I mean, I guess you could, but it just seems silly. And I know on my last test I gave a little bit of 100%, or a little bit of extra credit, but typically you're looking at 100%, and so I would treat it as a proportion out of 100%. So, but yeah, and it is a little tricky because typically, I mean, Rachel, I'm going to give you, you could make a case for it being a mean, but I would probably stick with proportion on that because it's out of 100%. So, and I don't think it would be terribly wrong if you did decide that, but a better example of a mean would be a mean stock return. Does that make sense?
Yeah.
Okay. Well, that was because you can't see my screen because I was just not doing anything. But anyway, all right, so let's go back to this example here. Pharmaceutical company has just developed a new antibiotic for children. Other similar antibiotics show 2% get a side effect. The FDA wants to know if the antibiotic is more than 2%. So we've decided the null hypothesis is P equals 2%. What would be the alternative hypothesis?
P greater than 2%.
P greater than 2%, 0.02. And why do you say greater than?
Because they said that they, something like they thought there would be more headaches.
More than 2%. Somebody can't see my screen? Still? Here, let me stop sharing and I'll start sharing again. Oops.
Wait, there's supposed to be a screen we're looking at?
Oh, you're not seeing my screen?
No,
Oh.
Me neither.
Sharing.
I thought we
Okay.
were just looking at your face. I didn't know.
Well, you were supposed to be looking at this screen here. So sorry, apparently I forgot to share. So thanks for, in fact, better than chatting, you should say, hey, I can't see your screen. Okay, so well done. Now you can see my screen, right, Faith? She's not going to answer. Oh, I forgot to ask this question. Is it a one or a two-tailed test?
One-tailed.
One-tailed. So, and in fact, it's a right-tailed test, right? Okay. All right. So let's go to the next one here. The blue book value of a 3-year-old Chevy Corvette is $37,500. Grant wants to know if the price is different in Miami. What would be your null hypothesis and your alternative hypothesis? And we should pick on somebody besides Tori and Rachel. And Corinne, I think you guys answered on the last one.
Oop, that was loud. Sorry.
Should I pick on somebody? How about Brooklyn?
Is it mu equals 37,500?
And why did you pick mu?
Because it's not a proportion.
Because it's not a proportion. Okay. And the alternative?
Is it mu does not equal 37,500?
You're asking?
That's what I would say it was.
And why would you say not equal to?
Because they're not asking if it's less than or greater than. It's just
Okay.
different.
Well done. And so is this a one or a two-tailed test?
Two.
Tailed test. Now, when it's a two-tailed test, what do you do with your p-value at the end?
Double it.
You double it. So you guys are going to be good. Not only do you study, you guys study hard. This is great. Honestly, I have to say, I think you guys are my best class in 7 years of teaching. You study more than anybody I know. This is awesome. So well done. Okay, let's do one more example here. The standard deviation of a 64-ounce bottle of detergent is known to be 0.23 ounces. The company wants to purchase a new machine. Dang it, I gave away the answer. And wants to know if there's less variability. What is the null hypothesis? Hopefully we'll pick up somebody that wasn't paying attention there. How about Jessica? But you're going to tell me you were paying attention, weren't you?
What was your question?
Okay, so can you see my screen here?
Yeah.
Okay, so the standard deviation of a 64-ounce bottle of detergent is known to be 0.23 ounces. The company wants to purchase a new machine and know if there is less variability. What would be the null hypothesis?
64 ounces. Mu equals 64 ounces.
Okay. Is that what we're testing?
It should be the sigma, I think.
Oh, yeah. Okay. Sigma equals 0.23 ounces.
Okay, sigma equals 0.23 ounces. And your alternative hypothesis?
Sigma is less than 0.23 ounces.
Okay. Everybody agree with her?
Yes.
Yes. Now you guys are lucky because we're probably not going to do any hypothesis tests on sigma in our class. But if you want to, take Math 2040 and we'll do lots of them. But that is correct. Okay? All right, so well done on those. Now, one other thing that I think the book talks about that we didn't talk about yesterday was type 1 and type 2 errors. Okay? And so a type 1 error this is what we generally refer to. In fact, here's kind of a little bit of a chart, okay? Either the null hypothesis is true or the alternative is true, okay? Our conclusion is we're either going to not reject the null hypothesis or we will reject it, okay? Now, it could be that the null hypothesis is true, we don't reject the null hypothesis, and that would be a correct conclusion, okay? It also could be that the alternative is true, and we reject the null, and so because the alternative is true and we reject the null, that would also be a correct conclusion. Now there are two ways we can make a mistake. It could be that the null hypothesis is true, but we incorrectly rejected it. Okay, so that would be a type 1 error. And we use alpha to represent a type 1 error. So that's one mistake that we could make. Okay. The other mistake that we could make is the alternative is true, but we did not reject the null when we should have rejected it. And that's what's known as a type 2 error. And we use the letter beta for that. Okay. So there are two ways to be right. The null is true and we don't reject it, or the alternative is true and we properly reject the null. Those are the two ways we can be right. Two ways we can be wrong. The null is true, but we incorrectly reject it. And so if we go back to the coin flip, because I think that's the easiest thing to do, okay? Let's do a coin flip. So we get 7 out of 10 heads. And that's kind of hard to tell if somebody is cheating, okay? So the null would be, it's a fair coin. The alternative would be, it's not a fair coin, okay? So the type 1 error would be to reject the null. Okay, so we said that it was a fair coin. So you and I are placing a bet. It's a fair coin. It comes up 7 heads, and you say, "Oh, Rick, I think you're cheating." You incorrectly said I was cheating when I was not cheating. Okay. So that would be your type 1 error. Okay. The type 2 error says, okay, we got 7 out of 10 heads, but Rick, I think you're a nice guy. You would never cheat. So I don't know. I think this is a fair coin. So you did not reject the null. You did not accuse me of cheating, but in fact, I was cheating. That would be the other kind of a mistake. You would say there wasn't enough evidence. 7 out of 10, that's a pretty small sample size. You say, you know what, I don't want to ruin our friendship over this. I don't want to accuse you of cheating because I value our friendship, but in fact, I was cheating. And there, maybe I put tape on the coin and it was an unfair coin. So that would be the type 2 error in this case. Okay. So now let's talk about real life here. Okay. So the question is, if you're going to make a mistake, is it better to make a type 1 error or a type 2 error? Okay. And so let's think about a real case. Okay. So the pharmaceutical company develops a new antibiotic for children. Other similar antibiotics, so 2% of children get headaches as a side effect. The FDA wants to know if the new antibiotic is more than 2%. Okay, so let's talk about this. So our null hypothesis is 2%. Here, I'll do this way. Okay. The null hypothesis says 2% of children get headaches, so 2%, and we want to know if more than 2%. Okay. So your type 1 error means to reject the null when you shouldn't. Okay. So in this case, if we're going to make a mistake, the type 1 says, let's say that the FDA says 2% is safe and greater than 2% would be not safe. Okay. So if we reject the null, then we think the antibiotic is not safe when in fact it is safe. Does that make sense? Okay. So the idea, let's say we're the pharmaceutical company. We've got a new antibiotic. We want to sell it, but we think it's not safe. We are not going to make money. Are not going to make money, right? Because we said our antibiotic was not safe, but in fact it was safe. So that's one mistake we could make. Okay. So type 2 error. Okay. Is to do not reject the null when you should. Okay. So in this case, if we're making a type 2 error, we say do not reject the null. Okay. So if we're going to make this mistake, we think the antibiotic is safe and sell it to the public when it is not safe. Okay. So the public sues us for sending a not safe antibiotic to the public. Okay. So let me ask you this question. You guys are the CEO of this company. If you're going to make a mistake, would you rather not sell to the public and not make money, or would you rather sell to the public and get sued?
You should do the type 1 error.
Yeah. Do you guys agree with that?
Yeah.
Okay. All right. And so, yeah, so that's the idea. So typically, type 1 error, this is what we refer to as alpha. Okay. And that's what we've up to now referred to as our significance level. Type 2 error is what's known as beta. And so most people, if you're going to make a mistake, you'd rather make a type 1 error than a type 2 error, because most people don't want to get sued. Okay? And so in this class, we are going to concentrate on type 1 errors, where in this case we thought it was unsafe, but it was actually safe. That's the better error to make than the type 2 error. And so if you wanted to do type 2 errors, you can take Math 2040. So I'm sure you're all signing up for that right now, aren't you? All right. Okay, so I think that is basically chapter 17. Okay. So I'm going to have to come up with a quiz by Tuesday. We'll do, so your chapter 17 homework and quiz will be due by Tuesday. And I think we're going to go ahead and move on to chapter 18 now, except for...
Rick, will this worksheet that you just did, is that going to be available to us? This one that you're on?
Would you like me to post this up there?
Yes, that would be awesome.
Okay.
Thanks.
I can do that, yeah. All right, so I can do that. Let's go ahead. I have a feeling my notes, I went over chapter 18 thinking I wanted to do this before. Here, let me just check something really quickly, because I messed up. I thought I think I've actually taught you a lot of chapter 18 as well. Let me just check one more thing here. Yeah, so we're going to start on chapter 18, except for I think I need to update my lecture notes a little bit, because they talk about both confidence intervals and hypothesis tests. Okay. So chapter 18 deals mainly with means. So I've already gone over all of this stuff here. All right, here's what I would like to do. Let's do an example. You know, to be honest, the chapter one, now that I'm looking at this, I need to update my notes. I think I've basically taught you both chapter 17 and 18. But this is a good example for chapter 18, okay? Now, if you have your previous outline, these notes are really similar, okay? So let's go ahead and what I would like to do is chapter 18. Chapter 18 focuses on the one sample mean with standard deviation known. So in a sense, this is going to be a really easy question because we're going to focus on, do you guys know what the equation is for a one sample mean with the standard deviation known? Maybe that was a bad question. Here's going to be, well, I'm going to give you two equations that you're going to want to know, okay? So it's going to be Z equals X bar minus mu divided by sigma over the square root of n. Okay, so this is for your hypothesis test. Then your confidence interval is going to be X bar plus or minus Z sub alpha over 2 times sigma over the square root of n. Okay, let me pull up your so just as a reminder, when you go to your announcements, most of you probably have it printed out by now, but we've got the formulas for tests and quizzes back on January 14th. Okay, chapter 18 is going to focus mainly on this confidence interval right here, that formula right there, as well as your hypothesis test right here. Okay. So what I'd like to do today with this example is we're going to take this example. Oh shoot, this is not the right example. My chapters are mislabeled. This is labeled 19, but it's really 18. Okay. We're going to focus on hypothesis testing for a mean. This is really chapter 18. I've got my chapters mislabeled. Hypothesis testing for a mean. So rules for the hypothesis testing for a mean. The sample must come from a simple random sample. The data must be independent. And the data should be normally distributed, no outliers, and your n should be greater than or equal to be 30. Now, smaller samples can be used, but a histogram or a QQ plot needs to verify that the samples are normally distributed. We haven't talked about how to create a QQ plot. But a QQ plot basically is how you can get away with small samples. I'm not going to worry about that. So in chapter 18, the first question you should ask yourself is this: do I know the population standard deviation? If your answer is yes, we're going to use the Z equation. If your answer is no, that's going to be the next chapter, which is the T equation, which is very similar. Okay, so this has got all the answers on here, but let's do this, okay? Let's do an example. The mean SAT score in 2007 was 515 with a standard deviation of 114. An educational psychologist believes that 4 years of English in high school will help students score better on the math, okay? Psychologist obtains a random sample of 40 high school students with at least 4 years and finds their math score is 540. Using alpha as 0.05, which is your type 1 error, find out if the psychologist's beliefs are correct. So we want to go through all of the 8 steps to solve this problem. And here's what I will recommend. When you're doing chapter 18, I would recommend that you do all 8 steps before you do whatever they ask, and you should be able, based on that, to then answer their question. Okay? So find all the values. Can I have you guys tell me what are the important values? Let's start with Carter. How's that? So Carter, the mean scores on the mean SAT math scores were 515. What are the values I need to know there?
So is it X bar? Is the mean?
X bar equals 515. Who agrees with Carter? Or who disagrees with Carter?
I'm wondering if it's mu.
Oh, thank you, Tori. Why did you say X bar there, Carter?
Because I thought it was just a sample, but is it the entire, every single person's math score?
Well, here, tell you what we're going to do. Let's keep going, and then you can change your answer later if you think that's wrong. Okay, how's that?
Well, I already think it's wrong because Tori's smart.
Tori's smart, but Tori won't be there to help you with your thing. So it is mu, okay? So so actually, here's your clue. You get a simple random sample of 40 high school students and find their mean score is 540. Okay, that's going to be your sample. Okay, so therefore this has to be the population. Does that make sense?
Mm-hmm.
Okay. All right. So way to go, smart Tori. All right. Standard deviation of 114. What is 114? We're going to stick with Carter.
Is it sigma?
Sigma. You said is it? You're supposed to say it is.
It is. Sorry.
Are you sure?
I think so. Yeah.
Okay. Why is it sigma?
Because that's the population standard deviation.
That's the population standard deviation. Very good. Okay. So the English teacher teaches 4 years of English. Is 4 years useful to us?
No.
No. It's good information though. Psychologist obtained a random sample of 40 high school students. What's 40?
N.
Okay. And is 40 with at least 4 years of English and finds their mean score is 540. So let's go back to Carter again. What is 540?
Is it that X bar now?
You keep asking questions. You're supposed to say it is. I'm the one asking the questions. I'm just teasing. Yes, X bar, because it comes from these 40, right? Okay. We're going to use an alpha of 0.05. So alpha equals 0.05. So we're going to find out if the psychologist's beliefs are correct. Okay, so we found all the values. That was step number 1. What is step number 2? Do you remember? Does anybody remember?
Can we find the null and alternative hypothesis? Is that where we do that?
That's step number 3.
Isn't it
Is
determined
find.
if it's quantitative or categorical?
That's right. Okay, so step number 2, is it quantitative or categorical? So let's pick on, let me see who else is in the room here that I haven't picked on. Okay, Caitlin, is this data quantitative or categorical?
This data is quantitative.
Quantitative. Boy, that's a loud beep. Okay, well done. Does anybody disagree with her? Okay. Step number 3, find the null and the alternative hypothesis. So the null hypothesis and the alternative hypothesis. Let's pick on, can't see here. Samantha, what's the null hypothesis?
Oh gosh, I'm trying to zoom in. The null hypothesis.
Are you on your phone?
Yeah,
Oh, I'm sorry. This has got to be hard on a phone.
it's okay. Would it be that this mu is no greater than 540?
So you
No.
already, so you forgot one of the rules.
Okay.
Where is my rule here? Rules for null hypothesis. Okay, so it's a mathematical statement, no change, no difference, fair coin. Always about the population. Oh, I didn't have it on here, but it almost always has an equal sign.
Okay.
Okay. So you correctly picked mu. It's almost always got to have an equal sign. So mu equals what?
515.
515. Very good. Okay. And your alternative hypothesis is what?
Is this one, is it still going to be equal or is it going to be the...
Okay, so let's go back to our definition. Alternative hypothesis, usually stated in the problem. And we have to decide, is it going to be a one-sided test, either right-tailed or left-tailed, or is it going to be a two-sided test? It's going to be a not equal to. So what does the psychologist think in this case?
Psychologist thinks that with at least 4 years, their SAT score is going to be 540. So it would be mu is less than or equal to 540.
Okay, so no. Okay.
No. Okay.
So she thinks that people will score better on their math. Okay. So we think that they're not going to be any different than 515. She thinks it's going to be better than 515.
Yeah.
Now, also, another couple rules. Alternative is always about the population, so don't be distracted by the sample score. Okay. Whatever number you picked in the null hypothesis, you get to pick it again in the alternative hypothesis, and you just have to say whether it's greater than, less than, or not equal to.
Okay.
Okay, does that make sense?
Yeah.
So because she thinks they're going to do better, she thinks it's going to be greater than 515. Okay?
Okay.
Another thing I like to tell people is don't look at your data when you make your alternative hypothesis. So you were getting way distracted by that 540, but don't look at that because we're only concerned about the null hypothesis and the alternative in this case. Okay, does that make sense?
Yes.
Okay. Step number 4 is what? Hopefully you guys are going to memorize that outline. Do you remember Waverly?
Yeah.
Now you got to pick the test.
Pick the test. Okay. Now, in this chapter, it's going to be really easy because we're always going to use this test for the hypothesis test, and we're also going to use, so this is one thing we can actually do it two different ways. We could do the hypothesis test, or we could do the confidence interval. So I would like you guys to get in the habit of being able to, we're going to do the same thing. We're going to do, so if the hypothesis test, we're going to use Z equals X bar minus mu divided by sigma over the square root. I forget the parentheses here. Okay. So that's the equation we would use for the hypothesis test. For the confidence interval, it would be X bar plus or minus Z sub alpha over 2 times sigma divided by the square root of n. Okay. Now, most of the time I'm going to focus on hypothesis test, but you should also know how to do the confidence interval. Okay. So now that we've got the test picked out, let's go with what's step number 5?
Find the p-value.
Oh, find the p-value. Okay, so before we do that, I guess we got to finish step 4. Find the p-value. Okay. So based on this equation now, who have I not picked on today? I think I've picked on everybody. Except for, no, I don't know, I've picked on everybody. I'll let you guys choose who wants to answer this question. How do you plug this into the equation?
Is it 540 minus 515?
Z equals 540 minus 515. Is that Rachel?
Yeah.
Okay.
Divided by 114 divided by the square root of 40.
Okay. And I need to put parentheses in here. Okay. So well done, Rachel. So here's what we're going to do. We're going to copy this into Excel. Okay. And paste. Is it going to work? Oh, it didn't. Why didn't that give me the answer? I thought it would. The problem with my formula? What's the problem? I got too many spaces in there? Oh, I know why, because it doesn't like, it thinks that's not really a minus sign. Okay, so I got a z-score. That's my z-score of 1.38, okay? 1.3869. Okay, so if I get, so this becomes a z-score of 1.3869, okay? Okay, so I've got my z-score. Now the next step is to find the p-value. So how do I, so I need to, so there's two methods with the table and with the computer. So how do I find the z-score? And also, what should I be doing? What do you guys think?
Does it matter which one you do?
So you need to do both. In the so if it's a paper test, you need to do the table, and if it's a computer test, you need to do the computer. So you need to do both methods.
So do norm s dist for the computer.
Okay. Now, there's one thing that I do, I'm going to close this, I don't need that open. There's one thing that I do think you should always do prior to doing the norm s dist, because the question is, here, I'm going to open this up. Okay, I think you should always draw a picture. You know what, I've got a finger here, okay? So this is going to be 515, and we got another distribution here. Whoops. Okay, my X bar is 540. I'm drawing with my picture, okay? So the question is, do I want to shade the area to the left, this area here, or to the right, this area here?
Isn't it to the right because the psychologist thinks that the test scores will be higher than the actual mean?
That's correct, okay? So I want the area to the, ooh, that didn't close very well. I want this area to the right, okay? Now, what's norm s dist going to tell me?
That's going to tell you the area to the left. So you have to do
left.
1 minus norm s dist.
Exactly. And so that's why it's important to do this. So if you do norm s dist of this score and you don't draw your picture, you will incorrectly think that's your p-value when it should be 1 minus that value. And so that's your real p-value. Okay? So your p-value with the computer is 0.087208, whatever that is. Okay? So with the computer, we get that value. And with the table, how do we get it with the table? My table, it's over here, okay? I got a z-score of I guess I'll round that to 1.39, right? So 1.39, where did my table go? 1.39, can't imagine looking at this on the phone. That would be really hard, Samantha. So 1.39 is going to give me this value here, 0.9177. And so once again, with the table, it's going to be 1 minus 0.9177, which equals 0.0823. Okay, so that value versus this value here. So they're pretty close, but they're slightly different depending on your method. Okay, does that make sense?
So which one do you want us to do?
So I want you to do this one on paper, and I want you to do this one on the computer.
Okay.
So, all right, I don't even want to think about our next test.
Do you always want us to do 1 minus the p-value to compare it to the alpha? Is that like something you do every time?
I didn't hear the last part of your question, Tori.
Oh, I just said, do you do that every time?
No, you don't do it every time, because that's why the picture comes in handy. Because if you had your alternative hypothesis was a left-tailed test, then in this case you would want the area to the left. And so in that case you would not need to subtract it from 1. And so that's where the picture comes in handy, because I know it's hard for students to know, do I subtract it from 1 or not? And that's why I say draw the picture. This one here on the left, yes, you subtract it from 1. This on the right, no, you don't subtract it from 1. So it depends, and that's why this becomes so important here, is to get your null and your alternative hypothesis right. If your alternative is greater than, you're going to want the red area on the right. If it was a less than, then you're going to want the yellow area on the left. And if it's a not equal to, then it could be either one, and then you get to double it. So, and so that's why drawing a picture is so important, and that's why I hit it, and students just hate to draw pictures. And so, anyway, I think if you draw the picture, it will help you decide if you subtract it from 1 or not. That's why I want you guys to draw the picture.
Rick, if the alternative hypothesis says H of A is mu is greater than 515, why did you shade it after 540 and not after 515?
Because this is my sample. My sample got 540. So we're comparing, in fact, maybe I better be careful here. So in this case here, the population is in black and the sample is in red. Okay, so we're trying to decide if under the null hypothesis, we think scores are 515. So what's the probability of getting a 540 if the scores are really 515? And the probability is very small. Well, it's 8%. There's an 8% chance you could get a 540 and be wrong, and it's really 515. Essentially, does that make sense, Rachel?
Yeah.
Because we're always comparing everything to the population. Okay. Now, okay, so we got 540. So 540 seems like a really good score, right? And so that leads us to the next thing here. After the p-value, what's the next step?
Compare p-value to alpha.
P-value to alpha. Is my p-value low? What do you guys think? My alpha, it's hard to see because I'm off the page here, my alpha is 0.05. Is my p-value lower than my alpha?
It is not lower than your alpha.
So no. So therefore, reject or do not reject.
I would say do not reject, right? Because if it's low, you reject the hoe, I think.
Perfect. Do not reject, that is correct. Do not reject the null, okay? So then the last step is to write the conclusion in English, not statistician. Okay. And so one thing so then we go back to the question is, find out if the psychologist's beliefs are the correct. The psychologist believes that 4 years of English will help students score better on math. Is the psychologist correct? That math scores are higher with 4 years of English. Okay, I want you to answer that question. What do you guys think?
Is it incorrect?
Why do you say that?
Because with alpha being at 0.05 and the p-value at 0.08, that means it wasn't statistically significant.
Okay, very good. You are definitely on the right track. Okay, now, so here's what's confusing, right? The students scored better. They got 540, which is better than 515. But we said that 0.08 is not enough evidence. So what we're saying is there is not enough evidence that 4 years of English helps students score better. It's pretty close to 5%, right? If we had gotten 0.0426, whatever, would there be enough evidence?
Yes, there would be enough evidence.
Yes, there would be enough evidence. So Tori's statement was a little bit strong in saying this. It's not that the psychologist is incorrect. We don't have enough evidence. Now, why not? Why is 540 not enough evidence? It could go back to your sample. Well, there's two reasons why. Number one, your standard deviation is pretty large. Number two, your sample size, 40, would you guys, if you were really doing this in real life, would you like to publish this in a journal with a sample size of 40? That's not a huge sample size, right? You'd probably want a few hundred students. So it could be that if your sample size was larger, that would help and there would be enough evidence, but we've got kind of a small sample size. Remember, 30 is kind of the lower edge. Obviously, you'd love to have as much data as you could get. So anyway, does that make sense?
And where does type 1 come into this?
So type 1 is your alpha. When we compare your p-value to your alpha, that's your type 1 error. Okay. We're saying we're willing to be wrong 5% of the time. But our p-value says we would be wrong 8% of the time, and we're not willing to take that chance.
Is our alpha going to be 5%? How do we determine alpha?
So alpha can be anything that you want in real life. The most common alphas are almost always 5%, but you can choose it. And typically, on a small sample like 40, maybe you could go, if your alpha was 10%, a lot of times you'll use a smaller alpha or a larger alpha if you have a small data set. So if we had an alpha of 10%, would there be enough evidence that this worked?
Yes.
Yes, there would. Okay. So you're supposed to pick your alpha before you do your test. The most common values are 10%, 5%, and 1%. Unless you're doing a genetic test, then it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So basically, remember that with an alpha of 0.05, you could be wrong 5% of the time. You're willing to be wrong 5% of the time. So it could be that the psychologist was correct and the math scores were higher. You just said there wasn't enough evidence. And so you might have made, you have a 5% chance of making an error. It could be that there should have been enough evidence that English helps students, but we just didn't find enough evidence. Does that make sense?
So how often will our conclusion be like, no, this is incorrect?
So let me just say this, on your homework, rather than making a blanket yes/no statement, you're going to hedge a little bit, and you're going to either say there is enough evidence or there is not enough evidence, because you could be making a mistake. Statisticians don't like to be saying that they've made a mistake. You say that there's evidence or there is not enough evidence of whatever you're trying to prove. And so, yes, there is evidence or there is not enough evidence of whatever you're trying to prove. Does that make sense?
Yeah. Can we have this worksheet too?
You can. And in fact, I think I already had all the answers there. I did. Oh, I have another example that I didn't have time to go over. Now, the other thing that I just wanted to point out is we didn't spend any time doing the confidence interval, but theoretically, you should be able to come up with the same conclusion. Obviously, you don't need to worry about a p-value for a confidence interval, but what I would like to do is to show you how the same problem could be done using a confidence interval. So in this case, and I know we're running a little bit short on time, so your X bar in this case is going to be your 540, right? So this is going to be 540 plus or minus your Z sub alpha over 2. Now, if my alpha is 0.05, I can look here on my chart here. That corresponds to 95% confidence interval, right? And so that's going to give me a critical value of 1.96. So 1.96 times your sigma, which Carter helped us find earlier here, which was 114. 114 divided by the square root of, in this case, 40. Okay, so I'm going to plug this in to my spreadsheet right here. So that was our thing. So we did confidence interval. So you got your lower and you've got your upper. I'm going to paste that. Oops. That's got a lot of spaces there. So we'll do the minus. Why did it do that? I forgot the equals. And we'll do the same thing with the plus. I'm going to change that minus to a plus. Plus, I say, equals. Okay, so now normally with our confidence statement, oops, I guess I better leave that alone. Okay, normally we would say we are 95% confident that the mean score of people with 4 years of English is between 504.7 and 75.3. Okay. Now let's answer the same question. Is there evidence that 4 years of English gives better scores in math? So what do you guys think? Based on that confidence interval, is there evidence? Remember, your null hypothesis is mu equals 515. So that's your hint.
Yes, there is.
Why do you say yes, there's evidence?
Because 540 is between 504 and 575.
Okay. See, I would have said no, there is not evidence, not enough. I mean, I should say not enough evidence that scores improve. And the reason why is because what you just said, Tori, 515 is in your interval. So we can't tell. So remember, these are your regular students. Your regular students are 515. And 515 is in your interval. And so we can't tell that the 4 years of English are any better. Now, if this had been 550, whoops, if this had been on the low end 550 to 575, 515 is not in there. So in that case, yes, there is evidence that 4 years of English improves because 515 is not in this interval. Does that make sense, Tori?
Kind of.
Yeah. So in both cases,
But with sorry.
Go ahead.
With
Ask your
540
question.
being in there too, then there also isn't evidence that it's doesn't. I don't know.
Oh, you're right. I probably shouldn't have picked that number. If this had been 530, we're going to pretend this is 530. So if your confidence interval was 530 to 575, so remember, yeah, 540, I probably should have picked a better number. So 540, your sample mean is always going to be in between these because you're adding and subtracting your margin of error. Okay? But it's the 540 doesn't matter. It's the 515 that matters. Okay? If the mean score is 515 and you get the lowest score you could get is 530, then yes, 4 years of English helps. But because 515 is in the interval, you can't tell if 4 years of English helps or not, because a regular student would be within that interval as well. Does that make sense?
Yeah, that makes sense.
So let me just tell you something. This is hard. Okay, I know that it's hard, and the interpretation right here, this is the hardest part. Okay. What's really sad to me is when students do all of the steps correctly, they get down here and then they write the wrong conclusion. It's like tripping at the finish line. But the conclusion is hard because basically you're having to take these numbers and you're having to compare them and then say, is there evidence or is there not enough evidence? And so typically when you're writing your conclusion, you don't want to say, no, the psychologist is completely wrong, because that's a little bit too strong. You're going to say that there is evidence or there is not enough evidence of the psychologist's beliefs. Okay? So I'm trying to decide. Here's what I want to do. Because I know this is hard. And I have another example here that I see here about the CDC and smoking. So here's what I would do, because I know we're way out of time. Homework is for chapter 17 is due on Tuesday for sure. I would like you guys to attempt to do 18. I won't make 18 due yet because I would like to do another example. We'll do this CDC example for next time. And I know, I purposely want to slow down a little bit because I know, because this is really where the class gets hard. And this is also where, you know, you guys are basically going to be taking your results and you're going to have to do these 8 steps. And I want you to do both a hypothesis test and a confidence interval and hopefully interpret them correctly. Okay. A lot of times what will happen is students will do the hypothesis correct and the confidence interval wrong, or vice versa. And I will say, do these agree? And even if you did one of them wrong and they don't agree, usually they should agree, but you should recognize when they don't agree. So anyway, I know this is hard. And so short story is, On Tuesday, we're going to do a quiz and homework is due on chapter 17. I would like you to start on chapter 18. I'm going to have chapter 18 due on Thursday, and we'll do another example like this on Thursday. Does that sound good?
Yeah, that sounds good.
Okay. So I will definitely post my chapter 17 notes up. And I may save 18 for Thursday before I post those, though. So, because I don't want to give away my second example that I have here. Okay. All right. So we'll see you all on Tuesday. And if you haven't collected your data, it's all got to be online collection from now on. And we'll talk. Actually, we'll talk more about that on Tuesday, since we're out of time today. So. See y'all on Tuesday.
Thank you.
Mm-hmm.